This video is going to talk about the problems for work and power. So the first one is on page 2 is the example. It says a 75 kilogram student runs up a 3-meter flight of stairs. That's pretty much just about the height between our first and second floor in this building in 4 seconds at a constant speed. What was the student's power output in watts and in horsepower? So this is pretty much going to be your lab. So when you do the lab, you're going to have to do something similar to this. So if I want to find the work, right, each time the student is going horizontally, there is no work done by against gravity, because the force of gravity is acting down. You move into the right, so there is no work happening in that direction because there is a 90-degree angle. But the work is only done when you're going up the stairs. So only the height of the stairs matters. And if you're going at a constant speed, the force you're applying up must be equal to the weight of the person. So this is going to be just basically Fg, which is mg, right, times all these heights added together, which adds up to really the overall height from for the whole stairs, from the bottom to the top. And this is just going to be 75 times 10, which is 750 times 3, which comes up to be, it looks like 2250 joules. Okay. Now, the power is the rate at which you do work. So it's work divided by time. So you just take 2250 divided by how long it took to do this, to go up the stairs, and you get some number in there. Now, to change it to horsepowers, you can just divide that power by 746, and you should get your horsepower. Now, another way you could have done power is just say, well, it's F times the average speed. Now, the force is 750. The average speed, we travel 3 meters in 4 seconds. And it comes up to be the same thing here, because now you're multiplying by 3 here, you're dividing by 4 down there. All right, let's look at the next problem, number 1. Okay, how much work is needed to lift an 18 kilogram box to a height of 4 meters at a constant speed? Okay, so again, work is equal to, if you're going at a constant speed, you're working, the force you're applying has to be equal to the mg of the box times the height that you're raising it to. So you could be going sideways and lifting it. Okay, you can be walking and lifting, or you can just lift it straight up. It doesn't matter. Each time you go in this direction, you're now working against gravity. So you can do the math here. So it's going to be 180 times 4, and you get what you get. The power is just going to be work divided by time. So you take whatever work you got here, and you divide it by 5 seconds. All right. Number 2. A 15 Newton force is used to pull an object 30 meters in 4 seconds. Now, you're not lifting it up, so there's no gravity involved here. You're just pulling it on a flat surface. So it's basically this, and they don't talk about any angle, so assuming that we're pulling it parallel to the surface. How much work is done? Well, work is F times the displacement, cosine of the angle between the direction of the force and the direction of travel, which basically in this case is 0 degrees. So it's just going to be 50 times 30, which is 1500 joules. Now, to find the power, you just take your work and you divide it by the time to find the rate at which you're doing work. An elevator can lift a 75 kilogram cart 6 meters in 4 seconds. How much work is done? Now you're going against gravity, so the work is just going to be 750 times the distance that you travel, and you going up, the force is up, and the displacement is up, so there is a 0 degree angle between them. To find the power, just take whatever work you got divided by time. All right, number 4, a 600 watt motor is used to move a toy car. the motor is used for 30 seconds. How much work is done? That's too easy. So power is work over time. Okay? So you have your power, which is in watts. You have your time in seconds, and you can just multiply. A lifter can press 100 kilograms in 0.2 seconds at a constant speed. When pressing, he lifts the weight straight up 0.8 meters. How much work is done? Now, the force that you're going to apply here is going to be equal to the weight of this 100 kilograms, which is 100 times 10. So that's the force. You're moving up, the force is up. Okay? You are looking at the force you're applying, not the force of gravity. Okay, or the lifter is applying. So it's going to be 1,000 times 0.8. To find the power, you just divide that by the time. These are considered extremely easy problems. Okay? All right. A 60-kilogram woman runs up a long flight of stairs in 4 seconds. So now, the only time she does work is when she's going vertically up. Each time she's moving horizontally, no work is being done. The vertical height of the stairs is 4.5 meters. What's her power? Now, I can do this two ways. I can find the work and then divide it by the time, or I can just do power is force times average velocity. Either way. So let's change that a little bit. Let's try it with the bottom equation. So this is going to be the force. Is going to be, since she's going at a constant speed, is going to be equal to her weight. Okay, and the V is going to be, she does 4.5 meters, the average V, in 4 seconds. And you can just multiply those numbers. Okay, a 1,500 kilogram car accelerates uniformly from rest to 10 meters per second in 3 seconds. Here, the force is not mg. The car is going in a flat surface. What's the work done on the car in this time interval? So work is force times displacement. Now the force is going forward, the motion is forward, so the angle is 0 degrees. So I'm going to skip the cosine of 0. The force is unknown, but we can probably figure it out by doing F equals ma. And we have the distance, or we can actually find the distance. So let's try that. F equals ma, so that's 1,500. They go from rest to 10 meters per second in 3 seconds. So the acceleration is basically a change of 3 meters per second in 3 seconds. So that's your force. So I'm just going to keep it like that. 1,500 divided by, or times 10 divided by 3. Now we need to find the displacement. I think we can use this formula here. Delta x equals, which I'll call d in this case. We're starting from rest, so the initial velocity is 0, so it's just going to be 1/2 the acceleration times time square. Or we could have done another equation. We could have done the one without the acceleration in it. But since we already have the acceleration, I'll use that. So 1/2 times the acceleration, which is 10/3, and in 3 seconds. So you would just come and just take that number, plug it in there, and you're good to go. To find the power, you just take whatever work you got here, right, and you divide it by the time. Or another way you can do the power is the force, which is 1,500 times 10 over 3, times the average velocity. Well, the average velocity is just basically 0 plus 10 over 3. So it's 10 over 3. Okay? Okay. Number 8, a man pushing a lawnmower on a level lawn applies a constant force of 250 newtons at an angle of 30 degrees downward from the horizontal. So they're pushing down in this direction here. Okay, so technically we should put this force here because we can't have the arrows going into the object. So this angle here is 30 degrees. This is your applied force. And you have all your other forces. Now the Fn here has to be bigger than the mg, because you're pushing down. So the y component of this fa, right, plus the mg should add up to n. And okay. So if I want to do so work is F times d cosine of, in this case, 30 degrees. So we're trying to find d. So the work is 1.44 times 10 to the third power over the force, which is 250 cosine of 30 degrees. Just be careful when you put this in the calculator. You put parentheses here. So the calculator will create parentheses here. You close it, and you put another set parentheses around the whole bottom. Okay, and the answer for that should be 6.65 meters. In that previous, in this problem number 8, we're assuming that there is no friction. Okay. And even if there is, I think it's only asking us for the work done by, not the net work, but the work done by the boy. A 3 kilogram block slides down a frictionless plane inclined at 20 degrees. So here's the block. This is a 3 kgs. The angle here is 20 degrees. If the length of the plane is, can't read that, is 1.5, so in other words, from here to here is 1.50 meters. How much work is done and by what force? Now this is frictionless, so let's do a free body diagram. So here is the mg, and here is the normal force, right? Should be a little bigger, but okay. Now the normal force doesn't do any work because it's always going to be perpendicular to the ramp. So the angle between the normal force and the direction of travel is basically 90. Cosine of 90 is 0 degrees. I mean, it's 0. Okay. Now we're going to try this without friction, and then we'll bring in the friction. So now the work done by gravity is the only work being done here. Now we can do this two ways. I can say that the work done by gravity is basically the force of gravity times the displacement down the ramp times the cosine, not of 20, but the cosine that these two, the FG and the D, make. So I'll call that angle alpha, I guess, right? Okay, so FG is basically mg, which is 30. We're traveling 1.50 meters down the ramp. Now, the angle that I'm looking at is, so we're traveling in this direction down here. The FG is here, so I'm looking for this angle here. Okay, so that angle is going to be the cosine. If this is 20, that angle will be, what do you call it, 70 degrees. Okay, so that's one way of doing it. The other way is you can break down the FG into its components. Okay, now this perpendicular component doesn't do anything. Okay, it's the mg sine theta component that does the work. So here is another approach. So the work done by gravity is only due to the parallel component, which is, now my force is no longer Fg, but it's mg sine 20. I'll just make that a 20. Times, we're still moving down the ramp 1.5 meters. And the angle between this force, this mg sine theta, and the direction of travel is 0 degrees. So which means cosine of 0, which is 1. And we should get the same angle, answer. Okay? And here, you probably know from your trig class that complementary angles, they swap the sine and the cosine. In other words, cosine of 70 is the same as sine of 20. All right, so let's bring in friction. Okay, so if we're going down the ramp, there is some friction up the ramp. Okay. what would be the net work done? So the work done here is just going to be the work done by gravity, which we found earlier. I have 15.39 here joules. Okay. And then we're going to find the work done by friction. Now, the work done by friction is the force of friction, okay, times still the same displacement. Friction is acting all the way from the top of the ramp to the bottom, times the cosine between the direction of travel, in other words, the displacement, which is down the ramp, and the force of friction, which is up the ramp. So that's 180 degrees. So friction is doing negative work because it's opposing your motion. So the force of friction is basically the kinetic coefficient of friction, mu k, times mg cosine of 20 degrees times the 1.5, and the cosine of 180 is negative 1. So now this is going to be 0.275. The mg is 30, cosine of 20 times 1.5, and times negative 1, of course. And the answer is negative 11.63 joules. Now to do the network, you just add up those two numbers and you should get about 3.76. Okay. And then later on, when we learn the work energy theorem, we can try to find the network a different way. Now here we could have done the work done by gravity. Okay. I think when we came up with the equation, it was mg times d, mg sine of 20 times d. Okay, now if you look at it closely, this is d sine theta, or sine 20. This distance here times sine of 20 is basically just the height. Okay, so going forward, the work done by gravity will just be mgh. Now it could be plus or minus, it depends. So if I'm sliding down the ramp, it should be a positive work because the mg and the direction of travel make an angle that's less than 90 degrees. If I'm going up the ramp, if I'm pushing this block up the ramp, the angle between the direction of travel, which is up the ramp here, and the weight, or mg, is bigger than 90. So I should end up with a negative work. But it's always going to be mgh. So you just have to make a decision whether it's plus or minus. Okay. If electricity costs 7.06 cents per kilowatt hour, right? Now this is not the energy for power. That's energy. That's not the unit for power. That's the unit for energy, right? Which is basically work. How much would it cost to run 120 watt stereo system 4 hours per day for 4 weeks? So now I think we have to find our energy in kilowatt hours first. So it's 120 watts, so which means 0.120 kilowatts. The time is 4 hours a day. So that's 20, so that's 4 hours per day for 4 weeks. So 7 days and 4 weeks. Okay, and we should get should get 13.44 kilowatt hour. Okay. Now if it costs 7.06 per kilowatt hour to find the cost for this length of time, you just have to multiply 13.44 by 7.06 and you get your answer in cents. Let's look at this conceptual stuff here. We got 3 RTs to take care of. Okay. So we need to rank the work done on the box by the force F. And again, we always talk about work done by a certain force. We can't just say work. Okay, if we say work done on a system, then we're talking about the network. Okay. Now, the work done on the first one is just F times 5. Okay. The work done on the second one is just F times 10. This one here is definitely going to be less than F times 5, because we're only looking at this horizontal component as doing the work. Okay? Or you can say, well, there is an angle theta here, so it's going to be F times 5 cosine of theta. Cosine is always less than 1, so that work done over there is definitely less than F times 5. The work done here is nothing, because the force is acting perpendicular to the direction you move in. The work done here is F times 5, but the force is opposing the direction of travel, so it's got to be a negative work. Okay, and the next one is just going to be 0, because the force and the direction of travel are perpendicular to each other, and you rank them based on this. See, here it doesn't say magnitude, so the greatest one, it looks like it's B is going to take number 1, then A will be 2, and then C will be 3. It will be less than F times 5, but it will still be positive. Okay? And then D and F will come next, and then E will be less because it's negative. Okay. So for this problem, I showed you earlier that the only thing that matters, okay, the only thing that matters for the work done by gravitational force is really just how high you're above your finish line, right? So the height is right here for both of them, right? So they are both at the same height. So you can do the math, but you're going to find that it's the same work done. So quickly, I'm going to do it on this side. So if the block is here, there is an mg acting on it down, okay, and the block is moving down. So let's just say it moves at distance d from here to here. This is the direction of travel. So if I want to find the work done by gravity, it's just going to be, let's call this angle here theta. It's just going to be this component, the mg, the work done by gravity. It's just going to be the mg sine of this angle theta times d, and that's it. Okay, and the mg sine theta and the d are both going in the same direction. So the other angle will be 0 degrees, right? Because you still have to do cosine of 0 here. Well, if you notice here, this d sine theta, this d times the sine of this angle is just the height. So this d sine theta is this much. And you can do the same process on the other ramp, and you're going to find that the work done is the same. So I think Ben is correct. All right, last one. So now we're pushing an object up the ramp. Okay, so it's got to be some applied force. We have our normal force this way. We have our force of gravity this way. And I don't know if they say there is friction here. All right, let's just, I'll come back to that later. I don't know. I have to, oh yeah, there is friction. It talks about friction down there. So maybe there is some friction here. Okay. The work done on the block by the hand, okay? Now, that's positive work, okay? The reason, because you're moving up the ramp, and the force is up the ramp, so that's a positive work. So this is positive, okay? The work done on the block by the normal force, well, that's 0. That's always perpendicular to to the direction of travel. The work done on the block by friction, that's going to be negative. You're pushing the object up the ramp. The force of friction is down the ramp. They're making a 180 degree between them. So cosine of 180 is a negative number. The work done on the block by the gravitational force. Now we can do this quickly. You can see that the gravitational force and the direction of travel right here, they make an angle that's greater than 90. So the work has to be negative. If you don't like it that way, you can break this force of gravity into components. Now the perpendicular component doesn't do anything. The parallel component is what does the work. So now the parallel component is going down the ramp, or is pointing down the ramp. The object is moving up the ramp. So it's got to be some negative work. And the net work done on the system, well, the net work is the net force times the displacement. Now the net force in this problem here is 0 because earlier in the text it says that it's going at a constant speed. And that's that. All right, see you later. All right, I'm out. Peace.